I don't know, cutting edge or kind of forward looking in terms of not existing yet and having the potential to enable a lot of applications and things like that in the future. But at the same time, because that's kind of the state that it's in, there's also many different definitions of what kind of a grid OS could be. So we'll start by kind of walking through some of that. We had our Grid Edge Executive Council meeting on Monday here, and the entire meeting was really about DER management, so distributed energy resource management. And as I was kind of listening to those discussions and listening to the speakers in that session, a lot of the things they were talking about were essentially kind of defining what a grid OS is, in my mind anyway. So that was kind of interesting, and we'll see what these folks think, in terms of like what their position on it is and how they see it going forward. So, just briefly, I want to introduce each of them, and then I'll have them spend a couple minutes each, kind of telling us more about themselves and their company. So, we've got Todd Headley, Executive Director of DVI. So, thanks for being here, Todd. David Kaplan is the CEO and founder of One Energy Systems, and Namish Patel, CEO of Gridco Systems. So, Todd, you want to start? Just tell us a little more about yourself and your company.
Sure. My company's DVI, and DVI is focused on helping utilities with system-wide voltage and VAR management for reasons for energy efficiency, demand response, reliability, and renewable integration. Our technology specializes in using AMI and the value it provides in terms of voltage and other measurements from every metering point. We take this information and intelligently manage capping controllers, load tap changers, voltage regulators, and some of the newer devices, smart inverters, battery systems. We currently have 11 customers in North America, and we're just starting to expand internationally.
Great.
David Kaplan, CEO of One Energy Systems. We're based in Seattle. We develop software for grid-connected energy storage. Our typical projects are megawatt-scale storage systems connected at distribution utility substations. And we've architected our software platform from the beginning to be generic, and so we're just now adapting it to handle other assets besides storage and to do fleet management across a variety of different assets, all focused primarily on the distribution utility use cases and sector.
So I'm Namish Patel, CEO of Gridco Systems. Gridco develops hardware and software to help utilities regulate voltage, manage reactive power, enhance power quality, particularly in cases where there's high PV penetration or a need to be able to extract more from energy efficiency programs or CVR and volt-VAR programs, and of course where there's power quality issues that utilities may need to contend with. So what we build is power regulation systems based upon power electronics, hardened for the distribution system, that last 25 years, don't require maintenance, in combination with controllers to enable the management of such devices through traditional SCADA systems, for example, and also to manage downstream assets, even assets that may be owned by the customer. And then we also develop a suite of software that support these systems in the field for manageability and remote control.
Great, thanks. Now I want to have each of you kind of give me and the audience your kind of definition or thoughts on what a grid OS is and how it might function. I know, Namish, you and I have talked about this in some detail before, so maybe you can kind of kick it off and let us know what your vision is for this.
Yeah, so I guess where I come, the perspective I come from with this is that, look, utilities already invest in a lot of software, SCADA systems, DMS, and for the most part, those work very well. The question is, what changes the nature of the use of that software that creates pressures and or challenges, technical and or economic, that would require utilities to invest in a different way in software? And so, if we go back to what those changes are, fundamentally, if I think about the core role of distribution operators, their role is the safe, reliable, cost-effective delivery of power. And what that entails is investments in capital, particularly capacity, to deliver power based on today forecasted demand. Now, of course, the thing that's changing this scenario, particularly in states that are seeing solar or adoption of EVs, for example, is the fact that the predictive aspect or the forecasting aspect of the job of the utility is becoming more difficult. It's becoming more difficult because they don't necessarily know where PV is going to be deployed. They don't necessarily know where EVs will be adopted. And moreover, both solar and EVs create a demand pattern that is significantly different from historical, significantly different in two very important ways. The first is there's a high degree of temporal correlation amongst both. In other words, when everyone gets home and they charge their EVs, you get a big load increase in the evening. Similarly, at solar, there's a high degree of correlation between the output of solar inverters at the peak of the day. And utilities have traditionally dimensioned the capacity of their systems based on some rules about the diversity of load. And as you decrease the diversity of loads in the sense that I just described, it makes the challenge of figuring out where to invest capacity far more difficult and unpredictable. And so if you couple that then with the fact that there's additional resources now associated with these the customer adoption of solar and of EVs that can, at least in principle, be under the control of the utilities, the basic technical and economic question becomes, how do I invest in capacity in the most cost-effective way while still supporting the demands of my customers? And that changes the primarily centralized paradigm of utility software, whether SCADA or DMS, today. If you look at a DMS system or a SCADA system, generally speaking, the number of elements that they need to control are somewhat limited. In our typical feeder, you may have half a dozen controllable devices, whether they're capacitor banks or voltage regulators or substation tap changers. But now, if we start to include the resources behind the meter that may be owned by the customer, smart inverters, EV chargers, demand response agents, home energy management agents, these resources now just in sheer number create a scalability issue for, frankly, any centralized software system. Moreover, the constraints in capacity in the distribution system are deep within the distribution system under these scenarios. For example, if you have too much solar in a particular secondary, the distribution transformer feeding that secondary could become overloaded, much as we're already seeing in places like Germany and Hawaii and even parts of California. Similarly, if you have a lot of EV adoption on a particular secondary, one of the first leading indicators of the problem is going to be voltage, but then the second problem is going to be overloading of existing transformers. So the piece in my mind that creates the need for something like a grid OS, and we can always come up with a different terminology for it, but in particular the need for something that's increasingly decentralized in its operation, is the fact that the constraints that the system operator now needs to meet are themselves decentralized. It's closer to the distribution transformer or on the primary, for example. And so now there's a need for sensors to know where those capacity constraints could be violated. And then there's a need for decision-making engine to be able to marshal the resources, both utility-owned and behind the meter, to be able to maintain reliability subject to the capacity of the wires that exist. And that, I think, is the essence of the grid OS. And there's multiple levels to the functionality that would be needed. Perhaps we can get into those later in the conversation. But at a basic level, you need communications to the endpoints, the devices you want to control. You need a means of understanding the topology of the system, that is to say, which endpoints could alleviate a constraint somewhere in the distribution system. And then third, you need a policy management system. In other words, as soon as you start to say, I could curtail a solar plant, or I could actively schedule someone's car to be charged, issues of fairness come up. And these are ultimately policy questions. So there needs to be a layer in this grid OS that takes care of the policy-related issues once you start to do these things. And we can get into more detail afterwards.
So it's not that dissimilar from like a control plane in a large communications network that you've worked on before, as we know. Interesting. David, you want to give us some of your thoughts?
Sure. My own perspective, my background is in system software. Been in the clean energy field for about 10 years, but prior to that in system software. And we've built our company with sort of two core competencies, one on the software side and one on the power engineering side. And I think this topic really brings together those two dimensions in a pretty compelling way. The kind of software we're talking about is an operating system in some sense, and it's probably an imperfect analogy in some others. But as we see it, there are a few basic things that have to be met by this emerging class of software out at the grid edge. It's got to be agnostic, first of all, on a couple of key dimensions. One is agnostic to the kinds of hardware that are out there, power system hardware that it's going to need to deal with, whether it be batteries, PV inverters, electric vehicle charging, et cetera. Agnostic across vendors, agnostic across class of devices. It also has to be agnostic, as Namish mentioned, to ownership. So in some sense, I mean, the ownership is a dimension that can be handled economically in various ways, if it's a customer-side asset versus a utility-owned asset. But at the end of the day, all of these things need to play in one connected power system, and they're governed by the law of electrical physics, and the control platform for them needs to be cognizant of that fact, therefore needs to be sort of agnostic of sort of who owns the asset, but able to control its electrical characteristics as needed and monitor the electrical characteristics. Another attribute that we see is it's got to deal with timescales in a fairly wide range, from sub-cycle through sort of second granularity and up to things like hour ahead and day ahead scheduling, which plays into what, from our perspective as a software supplier, is probably the key need that has to be met by sort of operating system software at the grid edge, and that is that it be able to actually harvest value for the system operator. So our sense is, I mean, clearly there's a set of incumbent utilities today who are customers or prospective customers for this type of technology. And however business models may change in the future, whether we go more toward a DSO type of model or something else, for example, there's still going to be incumbent grid operators who have the technology need to be able to manage the assets in this way. And I think a final thought that I would add is, from our perspective as a clean energy software company, we chose energy storage as a starting point to branch out from, because we see it as essentially kind of a superset asset within the whole mix. I mean, an energy storage system can inherently do almost anything that another asset could do on the grid. And so if you're managing that in a competent way, you can also apply the same kind of tools and techniques to managing other assets that might be out there as well.
Okay, thanks, David. Todd, thoughts?
Yeah, I'm going to focus a little bit more on the technology, how I kind of see that evolving over time. And so a trend today in grid operation is moving more intelligence up to the edge of the grid. That's kind of the theme of the conference here. The obvious example of that is microgrid technology. I mean, but there's some less obvious examples that are starting to emerge. I mean, the extreme edge of the grid is behind the meter. Home energy management system. I mean, that industry really hasn't taken off the way some thought it would. When it does start to emerge, I mean, I think you'll see names like Google and perhaps Apple, leading the charge, because their ability to engage customers for a new market is clearly proven. An example that is interesting in this area, Solar City recently announced they're going to give their next 10,000 customers a free Nest device. And the vision behind that concept wasn't just to have these two devices operate independently. The vision was, for example, when the solar PV production is at its highest, have that turn on loads within the house, the dishwasher, the washing machine, et cetera, instead of getting a price signal or some kind of notification from a centralized system. Just have all that intelligence in the home, in this example, in the Nest device, keep it local, so to speak.
Right.
Moving outside the home, kind of into the grid, into the neighborhood, the trend is towards more intelligent devices. You see utilities piloting these across the globe. Smart line sensors that can predict failures, by analyzing volumes of data in the field without sending it back to the utility. Utility scale storage, that can dispatch real reactive power based on the voltage it's experiencing locally. Smart inverters, low voltage regulators, being able to react more eloquently based on the transients they're seeing, in real time. Just a great new sectors of technology are emerging. And then, my vision kind of sitting on top and kind of at the system level, at the substation level and above at the utility, there's going to have to be an operating system that helps orchestrate these intelligent devices, really help the utility decipher where do they need to be placed. System-wide grid edge operating system will use AMI as a way to kind of look at the macro view of the system and identify what's happening on a real-time basis. Grid edge operating system on the system level will also aggregate these intelligent devices, for reliability and market purposes. And I think what you're going to see as we get more and more data available is that this system-wide grid edge operating system will rely less on a model and more on data it's getting from these sensor networks, to orchestrate the intelligent devices and really kind of better manage these modern distribution networks that are very dynamic.
Okay, great. So, the utilities that are on the path towards, just the building blocks before this even can take shape, right? They have enough challenge in, evaluating the right energy storage solution, evaluating the right distribution grid asset solutions based on whatever application you might want to name. In your discussions with customers or prospects, is this higher level coordination of these next generation devices, is that on their radar? Are they taking that into consideration when choosing vendors now, maybe from a hardware perspective that might have to operate in a more software-enabled system later on? I don't if you want to start, David?
Sure. Yeah, it is very much. In fact, we have active projects, funded projects now that are aimed very much at that. And we see it sort of unfolding in layers, kind of, at the topmost level, which I think you were alluding to, fleet management across a diverse collection of assets, not just storage, but PV inverters, demand response, other things as well, including sort of classic traditional utility distribution technologies. Site control, and I think it's been referenced in a number of remarks here, but the substation is obviously a strategic location where there's a concentration of assets, a concentration of control. There's usually networking, often fiber-based networking, back to the utility head ends. And then we see more and more being distributed out between the substation and the meter. I think that latter one is probably a pretty interesting open ground that utilities have done some experimentation in. Jason Handley, from Duke, who introduced this session, Duke certainly has a history of experimenting in that space. I don't think anything is concluded there yet by any means. And in fact, as we think about this concept of an evolving operating system at the grid edge, that's probably the most interesting innovation zone that we see out there.
Okay, great. And Namish, I know you guys are shipping units and deploying units now, and very very focused applications. But what are your kind of thoughts on are the utilities kind of understanding and seeing this vision and accepting of it?
If I had to name sort of near-term drivers that cause utilities to think about this grid OS concept, there's really three that I've been able to see. The first is around solar. Again, and there's two issues around solar: is can you harness the smart inverter either for some degree of voltage management, or at even higher penetrations of solar, can you harness the inverter to actually curtail real power from the solar system? The latter being particularly important in Germany, for example. And then the third one, again, not everywhere, but certain utilities are grappling and dealing with these issues, is EVs. And there's part of this that also relates to the economics. A lot of this, in fact, relates to the economics, which is, in California with DRP, for example, valuation of these resources is a prerequisite to being able to make a decision as to how you should marshal them. So I think that a lot of the economic discussions are being had in various states. Part of this is also, though, again, the policy aspect of this, which perhaps there's less discussion of now, but will become important going forward. As I had alluded to earlier, as soon as you say I am going to curtail a customer's solar output, or I'm going to actively schedule the charging of a customer's EV. Fairness issues really are important and need to be considered. But those are the three near-term drivers that I see. And in both cases, there's a combination of hardware and software that can help the utility manage the capacity and, as a result, reliability of the system in those three cases.
Great. One of the things, you were speaking on a session, on the crowdsource session earlier, Namish, and you were talking about dimensioning for capacity and kind of the worst case scenario of investing in copper and the challenges and the associated with that. When we look at kind of this growing disparity between kind of peak and average demand, like what does that mean for that problem, and can this address parts of that?
So, the peak demand that the utility sees on the distribution system drives, at a very fundamental level, the capital investments they have to make, right? This has historically been true for over 100 years. The average demands drive the utility's revenue, at least in a volumetric sales, volumetric revenue model. So to the extent that peak demand is increasing at a faster rate than average demand, you're getting this basic fundamental issue that utilities have to contend with, which is this disparity between revenues and costs. And what that really means is revenues and rates, because if you have to invest in capacity, that means that the customers ultimately are paying for it through rates. And so to the extent those are diverging, and in many places they are, both because of load growth but also because of solar, and also because of EVs, the basic question becomes, how little capacity can you invest in to be able to still accommodate the customer's demands? Now, there's basically three ways you could try to do this without asking the customer to make any changes to the way his or her demand is exhibited. The first is you could use storage, right? You could, if there's a peak capacity constraint at some point during the day, you could, at least in principle, if it was economic, you could use storage to try to move that peak. An alternative is you could try to, and that's sort of temporal shifting of power. You could also conceive of spatial shifting of power. If there's a particular feeder that has a peak during the middle of the day, perhaps it's from solar, a residential feeder with a lot of residential solar, you could, in principle, alleviate that peak by shunting power to another feeder that perhaps has a lot of C&I customers and therefore load at that time. That's sort of the spatial rerouting of load. And then the last thing you can do is use price. So there you can use pricing that varies throughout the course of the day to be able to induce a behavioral change amongst the customer. Now, of course, the last one is in some ways the lowest cost approach, but it does rely on customer behavioral change. And as of some states have seen, you have to be careful in designing your time of use schedules, because what you may find is that you don't reduce the peak, you just shift the peak. And so I think that's where this grid OS becomes very important, because in cases where time of use rates or time varying rates are not effective in getting a customer to make a behavioral change, then there needs to be something else that in effect can smooth out the demand profile. And I like EVs as the best example of this one. If imagine you get home and you plug in your car, and instead of you being involved in the process, you have a software agent that sits on your charger and says, I need to be charged by 6 a.m. because that's when I'm going to start my commute. Your neighbor gets home, and he says, well, I need to be charged by 10 p.m. because I'm going to go to an event that night. Well, why is it not that those agents shouldn't interact directly with the utility and let the utility, based on the capacity constraints it knows, schedule the charging of your EVs? And it may, if you want to have your car charged quickly, you may be charged a higher price than if you're waiting until, if you're okay waiting until 8 a.m. to charge your car. But nevertheless, that should be a model that's economically driven and demand driven. And that's something you can't really do with time of use pricing. And the same thing with solar. If there's a capacity constraint that requires some solar to be curtailed, there should be a contract with the distribution operator to say, okay, you can be curtailed by this amount, but there needs to be an OS, in effect, to be able to take all of those contracts, figure out who should be curtailed, subject to fairness considerations, and then go and actually execute it. So, there's a number of applications like this where a combination of hardware to shift the load without you relying on customer change, and software to induce, in effect, a change in the customer behavior to be able to always ensure delivery of power subject to the capacity constraints of the grid.
Right. Now, Todd, you mentioned earlier kind of, behind the meter, home energy management systems and other, assets. Namish mentioned inverters and EV chargers. So it's conceivable to kind of see how the utility might want to architect this, on just the distribution grid side. Mm-hmm. What level of participation are the assets behind the meter going to need to have? And it seems to me that there would be, some pretty, not simple interoperability issues and standards issues of those devices actually meaningfully participating in such an OS.
Yeah, I mean, there's a real good example of that. Enphase, the work they've been doing in Hiko, Hawaii, just the grid support they provided just by making a small change to the firmware on their inverter, which was behind the meter. It's a customer asset. But they showed the promise that how aggregating these small devices that aren't utility owned, can bring benefit to the grid. I mean, there are, however, still a lot of things to figure out that aren't just technology based. The economics. If you are going to start marshaling these resources for grid use, how does the homeowner get compensated? We're not talking about throttling their production. But if you are going to use their inverters for VAR support, there is a de minimis impact on the power production that does have to be accounted for, and the homeowner needs some incentive to participate. I think there's some work happening at some of the key utilities over the next 18 months where some of those questions are going to be answered, and hopefully the whole industry can benefit from that.
Right. Any other thought? Any of you two have thoughts on that piece of the puzzle, or?
Yeah, I would actually just second what Todd said. I think, particularly in these scenarios, you can't decouple the economics from the technology, because none of this stuff will take off unless there is some very clear either economic signals or service type that one adopts or buys into.
Right.
That sort of.
So that brings up another, maybe the next question. Maybe you can kick this one off, David, and if others have some thoughts. But, you can conceive of, such a control plane being developed and delivered and functional. But what are the linkages between that and the actual market, whether it be pricing or these signals that you're talking about? And where does that piece of this equation come in? Is that developed by vendors like yourselves? Is that developed by other parties, the utilities, and how does the market interact with the technology here?
I think there's a combination of technologies that go into that stack, and certainly a company like ours, in our current customer engagements, we're playing a pretty active role in that. Kind of the way we look at it is, and again, this maybe comes from our point of view of being focused on the distribution utility customer, is that the first task is to manage the circuit in a coherent way and to make sure that feeders are operating well, they're within voltage limits, that they're handling things like inrush of solar and that type of thing in as competent a way as they can, given whatever assets they have connected, be it storage or whatever else, or control of endpoint inverters. But in many cases, there's going to be excess capacity in any given time slice, or as Namish alluded to earlier, it could be done on a spatial basis as well as on a temporal basis. If you can shunt some value from someplace where it's not needed to someplace where it could either be needed, as on another circuit, or could be monetized if that distribution utility happens to be operating in an ISO environment, for example, then that's something that can be handled largely by software. And so we see one of the key missions of our platform as enabling that kind of split orchestration to take place. First and foremost, meeting circuit needs and maintaining circuits in as robust an operating profile as possible real time, but taking any kind of overage surplus that might be available and allowing it to be put into the economic realm, let's say, if the economic and market mechanisms happen to exist in that environment. The one thought I would add is that model plays in some places and it doesn't in others, and the US is probably as balkanized as any place in the world in terms of electricity markets or lack thereof, and so you can get a whole range of different ways that this plays out in different regions. Our view as a technology supplier is we want to produce technology that enables whatever operating and market models people have in their particular environment.
Right. You mentioned, you kind of piggybacked on what Namish was saying earlier about kind of the temporal and spatial shifting. Like, you can imagine the temporal shifting happening, through technologies like energy storage,
Right.
things like that. How do you see the spatial shifting actually being done?
Well, actually, it's being done in fairly simple ways today, simply by siting something like an energy storage asset at a substation on the high side of the transformer, so that the capacity that it makes available can be moved under utility control to need on 1 feeder versus another at any given time. And so more broadly, you can take and extrapolate on ideas like that and make them play over a broader class of assets as well. PV inverters, demand response, et cetera.
Any other thoughts, or you want to add anything?
Yeah, I mean, the economic indicators work on sort of fundamentally different timescales. There's the capacity value of a distributed energy resource. That is to say, what is the value over the long term of just having the capacity, whether it's used or not. And those necessarily better not change quickly. In fact, that's what this whole DRP stuff is about, which is how do you assign longer-term capacity value to a distributed energy resource. And those things drive long-term investments by the installers. They also drive dimensioning and forecasting and planning over long time frames for the utilities. There's also shorter time frame economic indicators, such as energy price. You could imagine energy price could be used as a signal to customers, much like time of use pricing is a time-varying economic indicator. You can imagine that energy price is used to either shape demand or even curtail supply in the case of PV. Imagine if energy price goes negative. People will shut off their PV systems because they'll be paying into the system to deliver energy. So I think it's important to understand the different timescales of the economic indicators and also what piece of software that those would have to interact with. You had actually brought this up earlier, David, and about the timescales that the grid OS would have to operate on. Our view actually is that you sort of don't want the grid OS to be operating on very short timescales, certainly not sub-cycle, and in our view, probably not even seconds, for the simple reason that bandwidth is a big constraint in utilities. If we were to build something that caused utilities to have to invest in more wireless capacity, and more bandwidth, that's a bad thing from my perspective. So you want to actually be using communications for relatively long time frame things, whether that's for day-ahead demand response, or whether that's for even emergency demand response, perhaps initiated by the ISO. You sort of want to be doing things, in our view, on the order of, at the lowest end, seconds, but probably more like minutes. And then relying on the hardware, the devices that are responsible for voltage control and ampacity control and so on and so forth, to do things autonomously on the very small timescales. So really the grid OS's role is in some ways setting the configuration and parameters of the various assets, utility-owned or customer-owned, but not doing things on very fast timescales or small time constants.
That's interesting. That leads into maybe my last question before I open it up to the audience for some Q&A. Given that, kind of this timescale issue and what system performs what functions, utilities are in the process or have deployed DMSs and are looking at DERMS, which this is kind of sounding like kind of a next generation version of that in some sense. What happens with those systems that they're just now ramping up and putting into place? What ends up? Where do DMS systems end up in this game and DERMS and those types of things? I don't know, Todd, if you want to start that one off.
Well, I mean, there's a lot of investment being made in those areas, and none of that's going to go to waste. I mean, I think you're just talking about another system sitting on top that's orchestrating the events. I mean, only one system can manage voltage. Only one system is going to manage the storage assets. Only one system is going to, Durham's is going to bid that capacity into the open market. I mean, I think the operating system we're talking about, I think, sits on top of all that.
Thoughts on that?
Yeah, I think I would just add that at the end of the day, all of these assets have to work in an integrated connected electric system that's governed by the laws of physics. And you want to, over time, break down the silos that exist across different asset management systems today that tend to be specific to certain assets.
Any final thoughts there, Manish, on that?
Yeah, just one, which is I think it's important we don't lose sight of the fact that if the grid OS, for whatever reason, were to go down, the power system better still work. Right. So that constraint in of itself suggests that there needs to be, as Todd sort of alluded to, some autonomy in the way that different pieces of the system are managed, independent of whether the grid OS is there. What the grid OS brings is optimality, right? And it brings enhanced reliability. But if it's gone, it better still work.
Great. We've got just under 10 minutes left, and I want to make sure to, give you guys some time to ask questions of these folks. So, who wants to start? We've got a couple mics in the room, I believe. So, anyone? Not a single question. There's got to be someone out there's got to start this off. I have some more, but I'd rather not.
So it sounds like all of you guys are implementing projects with a number of utility partners. When you go to utilities and you're not as successful, and they say, this isn't really a product that we're comfortable with now, or we're not ready to invest in that, can you help me to understand sort of what that justification would be so that we can sort of understand what the challenges are from a utility perspective in terms of investing in this?
All right, my view is pretty simple here. I mean, one, there's got to be a need. There's got to be something that the utility is contending with that they have a challenge dealing with the conventional mode. Second, whatever any supplier brings to the table better be more economic than the conventional mode. And if you look at it through those filters, it should be pretty easy to know where you're going to fail and you have at least a chance of success.
Yeah, and I would add that all of this is an incremental process. I mean, any technologies that we produce have to operate in an existing electrical system where the predominant mode is keeping the lights on day in and day out. And it's really a matter of meeting stepwise needs, some of which might be specific, as Namish referred to. So there's a particular need that has to be met at a particular location in a distribution system. Others of which might be somewhat experimental. So we also do projects where utilities are just trying to accustom themselves to new technologies like energy storage, or utility-owned inverters, for example. But over time, I think where we all want to go as an industry is evolving toward concepts like the theme of this panel, but that's a multi-year process.
Another question out there? I see Eric Gunther in the crowd. I'm going to put you on the spot and make you ask a question. You're never short of questions, Eric.
A couple of comments were made, regarding time frames and the like, and one of the things that we have, and specifically on the focus of matching supply and demand in an active grid, a lot of talk about, and we had, especially yesterday at the pre-workshop, on deploying microgrids, but we have those pesky laws of physics that we have to deal with being able to maintain that supply and demand. So let's talk about in the case of the microgrid scenario. And maybe I'll focus, I'll let whoever wants to respond here, but how are we going to bootstrap ourselves up or deploy in a greenfield all the technology that's necessary to make all those individual pieces work, and who's going to pay for it? Basically to respect those pesky laws of physics on how to make sure that microgrid will perform the way it needs to perform. And maybe put not much on the spot for that.
Okay, fair enough. Well, so microgrid is an interesting case to look at, Eric, because in some ways that's the hardest one. It's the scale, the small scale actually makes it the hardest one, because you don't get some of the benefits of law of large numbers that you might ordinarily in a large system, like a large utility-owned system. So the problem of supply-demand balance subject to voltage constraints and capacity constraints is indeed the hardest there. And it probably also means that the timescales it's got to operate on are also shorter than it might need to operate on a large multi-thousand node feeder, for example. Nevertheless, I think in a microgrid, though, the key piece in making it work is going to be dimensioning the capacity of the microgrid well from day one, so that the reliance on short time frame operations by the grid OS is at a minimum. Because as soon as you start relying on very quick control systems that are inherently decentralized, stability becomes a question. And so, but that's also where the cost of microgrids also increases, right? So this is the continual challenge of how do you balance capacity versus reliability. And if you want to skimp on capacity, you better be well prepared to take the consequences of a reliability, or at least a higher probability of a reliability issue.
Just a sort of quick follow-up on that. Have you found in the projects that you've been involved in that you're able to achieve that stability with static power converter connected energy sources only? And then I'll make a comment to your, depending on what you say.
So let me understand the question. You're asking about stability of power flow regulators.
In a microgrid, are you able to, in what you've been looking at, be it simulations or actually implementations, are you able to maintain the stability and performance of a microgrid with only static power converter connect device? In other words, inertialess devices only.
Well, so I should be upfront in saying that our focus is on utility scale things. So our experience with microgrids is close to nil. Let me put it that way. Of course, we have views on what it would take to do that, but perhaps someone else is actually better positioned, based on real-world experience, to be able to answer that.
We have a microgrid project in the works, and it's interesting actually to echo one of Namish's comments. In a microgrid context, something like even a few megawatt scale battery can have inertia, so to speak, if you're operating in the disconnected or the microgrid islanded mode. And so we found that deploying storage there along with a set of other assets, sort of traditional utility circuit management technologies and the rest, it's been quite a learning experience, but it's also informed a lot how we have begun to build out our software platform, because it brings in this sort of multiplicity of asset types and different devices, and you can do sort of more holistic management of the actual circuit that's involved. I don't know if that gets to your question, Eric, but happy to take a follow-up.
One of the things that we've found in our modeling and simulation, and in one big implementation at a large corporate campus, is that once you get to a certain size, we've not been able to find a way to make the system stable without having some rotating mass. And so I'm looking for others who are implementing, and when I say large, 20 plus megawatt microgrids, either behind the meter or on the utility side. And I'm curious as to if anyone else has begun to run into this problem. And although, yes, theoretically, you can simulate inertia with a power electronic device to a certain degree, and you can provide enough short circuit capacity to make protection work, so far we found we have to so greatly oversize the device that it's already barely economical, and now we can't make it economic at all. I'm looking for other implementations, other folks who have begun, who've seen this problem, and if there's any innovations out there on the manufacturing side, the innovator side here that you're represented here, to solve that problem.
Okay. Can't comment on that from our experience. The microgrid work we've done is smaller than that. In one case, there actually is a microhydro facility attached to the microgrid, which gives you some rotating mass, but not at the scale that you're asking about.
And I'll finish it off with one final question. Maybe Todd, you can take a stab at it. But given what we've just been discussing for the last 45 minutes or so, and imagine a progressive utility that's kind of already down the path of a lot of these technologies. When's a realistic time frame for a system like this to actually be functional and deployed?
Well, that's a tough question. What we are finding, however, the ones who have had AMI for 4, 5, 6 years, I mean, they're ready for some of these advanced applications. They're looking for the AMI system to be the foundation for their grid OS. I mean, just these sensor networks, getting a better perspective on what's happening, just through the AMI investment they've made. We see, the same ones that were early adopters for AMI will likely be the early adopters for grid OS.
Okay. Any final thoughts from your perspective on timing for these types of things?
Generally speaking, I agree. I think the first instantiations of GridOS we'll see will be versions where it's primarily utility-owned devices that are being controlled, for the simple reason that it's under the utility control. The customer-owned assets under the control, as we alluded to before, really require regulatory change, or at least a rate design change within the context of an existing regulatory framework to be able to really drive that problem to scale. I think probably the first thing that actually occurs is the need for some sort of interaction with what I'll generically call aggregators, whether that's the Nests or Googles or the Enphases for that matter, to sort of marshal the behind the meter resources for the good of the grid. But that still requires some sort of rate, some sort of regulatory solution to the economics problem.
Right. All right, well, we're just a couple minutes over, and I don't want to eat into the next session too much. They're going to come directly here, so if you're interested in this session, please stay. And let's thank our panelists for being here.